Very, very good. What test?
Spark.
Spark. Which one? This one?
Share. Make it the other way, no?
It's okay, let's
Is that
still 80%.
you can do like this.
Mm.
Let me do that.
Okay. Thank you. Battery
Tak pakai.
auto okay.
Battery, yeah.
Mm-hmm.
Okay. The flow map, yeah, you might see some petal analysis, different color, different flow rating, you can see the different colors. So the triangle is the one that we, the solution for that calculation zone. So that's the line is the possible solution. So you will see the possible solution. So it could be this way, that way, depending on the PSH is the similar percent. QL divided QH divided by area total. So yeah, so depending on the velocity here, velocity of light phase, velocity of heavy phase, it will be seeing at which flow regime. Yeah. So you can see the different flow regime. So on the zonal improve, so you can see we input the Q on surface, but we don't calculate, yeah? We don't use for calculations. We for the start point, maybe yes, but not for calculation. So we do have some tool reading. Y water, YG, Y water from capacitance, for example. Yeah. YG from GST or from optical. PM, where? Your spinner. Yeah. PM is from the calculated PM. Or you might have some direct calculation of PM. You can have velocity oil, velocity water, velocity gas. Velocity water you might get maybe from your RST water flow law. So you directly get water velocity. Or gas velocity, oil velocity, you have some different type of pressure. So you put a chemical dissolving oil, so you know the distance, you know the time, you know the velocity. So that's different type of 2D, right? Density, you might have the RFDC gradient deviations. Temperature, your temperatures, platinum resistance. So you have everything here. Emerald is not using that one. Emerald tried to simulate the same response using this VPGF, using the snippet that we have chosen. And of course, if we do the temperature modeling and the friction, the relative characteristics, yeah. So we calculate based on the model, the model or simulated response of the two. Then we compare our model, like we see on the spinner, we have the green line and the red curve. So we try to put the green on top of the red. So this is the one. So this is the green line, this is the red line. So we like to get the green line on top of the red. How? By minus. So this is error minimalization. M1 is measured, big M is model. So it's just error minimalization. You can just do some non-linear regression. So we might change some of the friction, we might change some of the PPGF or change the correlation in order to match this to that. Yeah, you can do. So then you do it for each calculation zone at the same time. So we Emerald not using the measured data, but Emerald is trying to make the model close to the measured data with the error minimalization. That's why you can see the error, 100% error when you get very small or not closer. So that's the error. So you do it quite quick, yes, computer. So you do very quick on that one. So you do for its calculation zone. Yeah, in the zone method. If you use continue, that temperature, you do for each different sampling. Okay, so this one, I think I like to, yeah, you can do that this one easily. I think I like to draw, it's better to draw. To make it quicker. I like to
You beli kopi apa?
Americano.
Yeah.
Okay.
Ini I beli tadi tau.
Okay. You cakap no sugar ke macam mana?
Memang ni sugar tu bila dia bagi.
Terlampau manis.
Tambah lah air panas.
Tak apa.
Okay, so I don't know. Can you see this
Yeah,
one?
yeah.
This one?
Okay, it's okay.
Right.
The TV-nya, okay.
So, for example, this is the hold up. Heavy. Starting from 0. Yeah. And this is Q heavy. Okay. This is the hold up heavy. For example, no hold up heavy, so it's all light phase. It's 0. The maximum hold up heavy is 1. Yeah. Cannot be higher than 100%. Agree? So this is Q total. So from to 1, just draw a line. Something like this. So for example, if there is no heavy phase, just light phase, no slip phase. Yeah, that one. If total heavy phase, no light phase, there will be no slip phase. And you can just draw a line. This is no slip phase. So if hold up is 50%, yeah, so you can draw like that. So this is Q heavy, this is QL. So the heavy phase will be 50%. That will be 50%. It's linear function. Yeah, it's linear. So if there is no slip, easy. You can just directly calculate hold up to cut. Yeah, it's easy. But liquid is fine. You might see like this. Oil, water, oil, you might see like this. So it's quite straight line. We'll see that. But if you have with the gas, so for example, this one gas and this is water, you might have some slippage. So what the slippage is, something like this. Yeah. So when you have the slippage P higher than 0, so the hold up you see is higher than it should be. So for example, something like this. Imagine you have a tube. You have gas and water at the same time with the same speed. So it's okay. But when your gas is faster, at one depth, the gas hold up has speed gone up. So the water hold up here is higher. Right? So that's why if you have slippage, the heavy phase hold up is higher than if there is no slippage. So you might see something like that. If there is no slippage like that, if you have slippage, your heavy phase hold up will be high. So depending on the flow regime. Depending on the flow regime. If you are dominated by the heavy phase, but very small amount of light phase, what kind of flow regime? Heavy phase, small gas. What flow regime? Gas velocity is small, gas hold up small. Which flow regime? You see, gas velocity low with flow region on the left. What type of flow region is that?
Bubble flow.
Bubble. Yeah, bubble. Yeah. If you are in very high light phase, very high gas, very small liquid, what type of flow regime?
Very high gas slug. Slug.
No,
High gas.
not high gas, small water, very small water.
Mist.
Mist.
Miss. Okay.
Yeah. So yeah, either after bubble you might be having like a slug, or you might have a bigger like churn flow, etc. You might have some different things.
Change flow. Okay.
Yeah.
Oh, slug minyak banyak. Fluid banyak. Okay.
So you have a different flow regime, a different percentage or holder. Make sense?
Mm-hmm.
Yeah. And in the one flow regime, you have the formula for slippage. So in the one flow regime, you will be having straight line. In the other flow regime, you have another straight line. You have another straight line. You have another straight line. Straight line. So it's not continuous.
Different slope.
Yeah, different slope. So the transition will be in between, yeah, for examples.
Mm.
So that's the how to look at the slippage. Yeah. So we know the hold up, we know the slippers, we know the Q. We choose the slippage correlation. So for example, we have 0.5, we choose the flow correlation. Intercept is here. So I put that one down. So this will be my Q water. This one total there is Q gas. Yeah. So if we have slippage, of course, the light phase rate will be bigger. Then there is no slippage. Yeah. If we have density, not hold up. For example, we have density. So I replace the hold up with the density. So density water, raw water, maximum. This one, raw gas. From where? PVT. Yeah, the endpoint here and there, maximum is from PVT. What we are measuring here is from the tube. So as I mentioned yesterday, I need to put that one end, two ends, according to the density of CO2. This one will be modified by the tool reading from to air 100% gas. This one is from modified by the raw tool at 100% water. In that case, then I have the endpoint from the tool and the measured point is from the tool, so it's okay. Yeah. So you do it for every calculation, so at once. I wrote this fast. That's how we do in Emerald. Yeah. The QT, the endpoint is coming from where? From VM times area. Yeah. For each different calculation zone, we have a different VM, different QT, different endpoint, but this and that according to PNT. Yeah, it's the same on the picture here, but I like to explain early, I mean, easier using the pictures. But this is really similar on that one. So you might have a different sleep aids there. So increasing sleep aids, you have a different flow regime, something like this. At the end is this is raw gauge. It's calculated, you have PQ, right? You water Q or gas. So yeah, you might have density from the two, but some this is density calculated from the hold up. If you have hold up, you have raw error at from PVD, hold up from capacitance, you get the density and you can put that one in. Or yeah, you can have hold up directly 0 to 1. Same. So minimum 0, maximum 1, minimum raw gas, maximum raw water or raw oil. If you are in 3-phase, you do it twice, yeah. So the split between total liquid to gas and between oil and water. So there are 2 times calculation. So this is it. This is the one that we are in ML.
This is the one we did yesterday, right?
Yes,
Well,
but we are looking at only at the end point because there is no edge, right? It's all gas. But then if we have density, then we might have something. Yeah. So yeah, we'll see this one on the exercise. Maybe it's easier to explain rather than looking at this one. Yeah. So this is a 3-phase. So you might see there are 2 steps there. So total liquid with the gas with weights and then split bed oil and water. So there are 2 steps. Some of the correlation they do it at the same time. Okay. So this is the answer for MR multiplications here. How to choose the correlation? So first, try to get the same for prosper or nodal. So we can ask the client or PE, they use which correlation, and we try to use the same. Okay, second one, local empirical experience. So if somebody has been done emerald using that correlation and it was, correct, it's the same with the surface measurement, surface rate, then we try to continue using that correlation. Deviation or not, some of the correlation is dedicated only for vertical, so we need to choose if it is applicable or not for deviated wells. Based on scientific principle, this is difficult. So it's really depending. Yeah, I usually don't look at the scientific principle. So just look at the Prosper, so what they use, and also the match to the surface. If you believe on the surface rates, of course they have this range of error, right? But if they are okay, you can put benchmarking on that one. Then you try to choose the correlation which gives you quite close to the surface phase measurements.
How many
10%.
10% difference? Okay.
Yes, 10% different, more or less okay.
Okay.
Yeah. But then you need to know the limitation of surface rate as well. yeah, some like in Petronas, the gas is not dependable at all. But liquid usually is pretty good because they use separator or MDFM, yeah, multi-phase flow meter. So usually it's pretty accurate. But of course, you might compare. But if you believe, I mean, if your spinner, you have a good slope, good threshold, and I know my spinner is good behave, then if the difference maybe 20% or more than that, so just give the same. I mean, just put on the report.
Okay.
My spinner is giving like this.
My spin is good.
Yeah,
Wrong.
yeah. I mean, this is the calculation,
Yeah.
right? So there are some variables, but our spinner is okay. So we might try to what you call it to calibrate their surface measurement. It might be happening, yeah. When I was in Total, I guess, yeah, I do a lot of Emerald because we do have some project that have a lot of backlog of PLT, so we do that one. And I don't remember, but there are several wells, but one of the well, I use almost the same slope for all the wells. And one of the well, the reading is very different with the surface. So I don't want to change because I know my slope. The tool is the same, right? So give to them and okay, then after that maybe a month or 2 months later on, they found out that the calibration is not good. I mean the what you call it, the venturi.
Okay.
They change, I mean they have a different venturi but they haven't calibrated. That's why it's not accurate because you have the range of the what you call it, the breadth, the cube of the glass. So if something like this could happen, so yeah, do not always match to the one they have.
If it's too far,
Compare, okay. Compare if too far, yeah, you need to question mark on that. So what could happen?
okay.
Yeah, if the client tell that okay, so you cannot rely on this measurement, so that's okay. Yeah, something like that. So yeah, usually I try to match the one that surface if you can rely on that surface. Yeah. And particular correlation might be because of failure. I'll actually show you this. Yeah, some of the correlation they are not really
Suitable.
yeah, suitable because this one you have some slope, right? So you have different like this, yeah. You have the slopes, but some of them they are very straight line at the beginning. So you have something like this. So when you have density maybe 0.5 or 0.1, 0.2, they're all giving the same. Was a straight line. So I'm not using this correlation. I try to use the continuous one. So when you have a density here like this, you have density low, you have a low heavy burst. So if you find that's why when you look at the table, there's an error. Error can be minimized, but please look at the plot as well.
Okay.
So we'll see what it intercept or what the correlation you use. So if you have something like this, then I'm not choosing that one. I'll let you use the one that has some linearity on that. So that's the one. Constant slippage. Yeah, it's difficult to get that one, but if you are in the multi-crop tools, you don't really need to have the slippage, so just put constant slippage, so you don't need slippage. There is no tool that can measure the slippage velocity at the moment. If you can find that one, you'll be very rich, I guess.
Yeah.
You're replacing emerald.
No need to calculate.
Okay. So that's it for multi-phase theory. So far, okay, right? Not very complicated.